Do you feel the vibes?
Hi everyone, I hope you all had a wonderful, relaxing break. I know it was way too short. But exciting things. We are starting with chapter 3, exponential and logarithmic functions. We're going to start with exponential functions first and then move on to logarithms. Yay! Okay, so let's get started. Exponential functions. So these are functions that basically look like this. F of x is equal to 4 to the power of x. So now it's the variable that's in the exponent, right? And the base is a constant. So until now, we had things like y equals x to the power of 2, variable base, and then the exponent is a number. Now we're going to switch that up. So it's going to be something like y equals 2 to the power of x, right? So the variable is the exponent. Examples of exponential functions are, like this one, 3 to the power of x. It could be 1/2 to the power of x, again, a constant to the power of x. It could be e, remember e is just a regular old number, 2.7 to the power of x or x minus 1, right? These are all examples of exponential functions. So before I move on, right, it's important here, I always like to make the distinction between an exponent and a power, right? The exponent is the number that basically is written as a superscript, right? So if I have, for example, 2 to the power of 3, the 3, we all know, is the exponent, right? When we do that math, we get 8. 8 is the power, right? So it's the power of 2, right? To the power of 3, right? Like it's to an exponent of 3. So if I wanted to talk about what are the powers of 2, right? 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. So these are the powers of 2, right? 2 to an exponent of 4 is 16, and so on. And if we were to go in the other direction, right? 2 to the power of 0 is 1, right? But 2 to the power of minus 1 is 1/2. 2 to the power of minus 2 is 1/4. 2 to the power of minus 3 is 1/8. So all of these are the powers of 2, right? Just making that distinction between the word power and exponent. All right, so what is the deal with exponential functions? The thing with exponential functions is they model situations which increase or decrease very, very rapidly. These are graphs of exponential growth and exponential decay. And just by looking at it, you can see the graph on the left is growth because it literally goes up, right, from left to right. And then the other one is exponential decay because it decays or decreases as we go from left to right. Well, what makes it exponential is the following. If I choose a random point x, this is its corresponding y value. And if I pick another one relatively close to it, x2, this is its y value. Now, if we compare the y values, look at what a bigger difference there is in the y values compared to the difference in the x values. In other words, if I just go from one value to a very nearby value in x, the y value changes a lot more rapidly, right? So a very little change in x produces a much higher change in y. In other words, again, a very little time can go by and a really big change can be produced. My go-to example to this, right, is you go out, for lunch or whatever, you hang out with somebody who's sick, and then within like hours you are just as sick and like incapacitated basically, right? So what happens, you get like a few germs from them into your body, and then within hours they multiply at, for lack of a better term, exponential rates, and now they've just like grown to such a higher number. That's exponential growth. And then you go to the doctor, gives you antibiotics, take one pill, takes two pills, and then all of a sudden, poof, like they're all gone, right? They exponentially now decayed as fast as they increase. So that is a good example of exponential growth and decay. We're going to come across so many other examples. Okay, so what do we know about exponential functions? The most important thing is that exponential functions, when you graph them, have an asymptote, a horizontal asymptote, right? That means the graph comes very, very close to that asymptote, but never really touches it. So in the case of the bacteria in your body, yes, they increase, but they start from zero. Can you really say you had zero bacteria in your body? Not really, right? And when you took the antibiotics, did it kill every last one? Not really. Close to zero, but not all. Hence the asymptote. Okay, so my classic example of this is this. If you ask me to draw a bunny rabbit, I can't draw to save my life. But if I were to draw something, I would at least have to put what on there? The ears, right? Without the ears, it is not a bunny rabbit. An exponential graph without the asymptotes is not an exponential graph. It's just a curvy line. Okay, all right, so let's do it justice. Okay, so let's talk about domain and range. Domain, remember, is all of the x values in an equation that you can plug in, right? So if an equation is something like, let's say, y equals 2 to the x, you can plug in any x value and it will give you a defined y value. So the domain is all real numbers, both for exponential growth and for exponential decay. The range is going to go, in this case, it's 0 to infinity. This number is always going to be the horizontal asymptote. So here too, from the value of the horizontal asymptote, we're either going to go up to infinity or down to negative infinity. The y-intercept is 1. We're going to go over this. So in this case, there is no x-intercept because that's where the horizontal asymptote is. Let's talk about end behavior. In the case of exponential growth, as I go to negative infinity to the left, right, f of x approaches 0. But as I go to positive infinity to the right, f of x approaches infinity. In the case of decay, right, as I go to the left, f of x approaches positive infinity, and as I go to the right, as x approaches infinity, f of x approaches 0. Okay, this brings me to another very important point. You can look at these two and you can clearly state, like it's not really that difficult to say that the one on the left is growth, the one on the right is decay. But let's really say what exactly is happening. In the case of exponential growth, as x approaches infinity, right, as we're going to the right, the graph moves away from the horizontal asymptote. In the case of exponential decay, as x approaches positive infinity, the graph will move towards the horizontal asymptote. Okay. And of course, exponential graphs are continuous everywhere. Okay, fabulous. Yay, let's move on. So we know how to tell if a graph, if a function is exponential growth or decay if we have the graph of it. But what if we only have the equation? Well, in that case, you have to look at this number b. B is the number that is raised to the exponent. And when we're doing that, we're going to ignore any negative signs. Okay? If that number b is greater than 1, then it's exponential growth. And if it's between 0 and 1, it's exponential decay. All right, so let's take a look at some examples here. This one, 2 to the x, this is the number that gets the variable exponent. It's greater than 1, so this is growth. 0.5 to the x, decay. 1/3 to the x between 0 and 1, decay. Okay, what about this one? This is 1/4, great. But it's to the power of negative x, right? Our form is that x has to be positive. So how do we get rid of that negative exponent? Well, we have to write this as a reciprocal, right? 1/4 becomes 4 to the power of positive x. Now we can clearly see that it's growth. Okay, so again, you ignore any negatives or, so for example, y equals -3 to the power of x. This is still growth because I just look at the 3 without the negative. Okay, if I have y equals 3 times 1/4 to the power of x, just look at the number that's being raised to the exponent. 1/4 is between 0 and 1, so this is decay. Okay, let's graph a couple. So this one here is a graph that you should be able to do without a calculator. I have f of x is equal to 2 to the x. I first of all, I just identify growth, right? Okay, so the asymptote is y equals 0. It's going to be y equals 0 unless there is a vertical shift, +1, -2, and so on. So this is y equals 0. The y-intercept, we know how to find y-intercept. It's f of 0. So that's 2 to the 0, which is 1, right? And we can write that as a coordinate. Okay, to graph this, let's go ahead and put that asymptote. Remember, bunny ears. All right. We're going to pick points, right? Basically, these are going to be the powers of 2, like we talked about, right? So, 1, 2, 4, 8, and so on, -0.5, and so on. If you want to pick points, these are the points that I usually pick when I have exponential growth. Remember, you always want a couple of positives, some negatives, a 0, right? And with exponential functions, the numbers really tend to get too fast or too small too quickly. So this, I find, is pretty good most of the time. So it's like my go-to points for growth. Okay, so 2 to the -1, a half, that's one of the powers of 2. 2 to the 0 is 1, and then the other powers of 2 are 2 and 4, and so on. So let's go ahead and graph this. This is a half, then 1, that's the y-intercept, 2 and 4, and then we go ahead and graph. Remember, this is not connect the dots. We have to go up to indicate that it grows exponentially, and here to indicate that it follows the asymptote. And there you have it. Yay. Okay, domain is all real numbers. We're not going to think about this. The range starts at the asymptote, and because this sits above, it goes up to positive infinity. Left end behavior, as I go to negative infinity, y's approach 0, and here infinity, and it's continuous everywhere. Okay, fabulous. Let's move on to the next one. All right, 3 to the power of -x. Okay, remember this is decay, right? Remember we can write this as 1/3 to the power of x. It's decay. Okay, so the asymptote is, again, y equals 0. The y-intercept, f of 0, is 1. You can either write it like this or you can write it like this. I actually do like the, I don't know which one I like. Well, it's Sunday as I'm doing this. So I guess Sundays for intercepts. I don't know. Okay. This is decay, right? For decay, because it's like everything is switched around, I like to use -2, -1, 0, 1. Again, not set in stone. You could use 154 for all, if you want. But I just choose numbers that I can get some points out of. At least 3 numbers 3 points on a grid is what we're shooting for, right? Okay. So 3 to the negative x, so this is 3 to the negative 2. So that's 9. 3 to the negative 1, 3. This is 1. And then 3 to the minus 1 is a third. Okay, so at negative 2, we're up at a 9. Then 3, 1 and a third. Asymptote. Bunny ears. Okay. Fabulous. All right, you can put the arrows. You don't have to put the arrows. It's up to you. Domain. Range. Okay, so end behavior. On the left-hand side, it goes up to infinity. And on the right-hand side, it approaches 0. Remember, it decays towards the horizontal asymptote. And it's continuous everywhere. Fabulous. Okay. Transformations. Same sort of transformations apply, right? So remember, in the case of, the parabolas and all the other stuff, same thing. So here we have the blue is f of x equals 2 to the x. And here when I have g of x equals 2 to the x plus 1, right? This is similar to having, like g of x is equal to x plus 1 squared. So the graph moves to the left. Okay. Here I have f of x is 2 to the x. H of x is 2 to the negative x. So this is f of negative x. And do you see how this is now a very clear example of reflection around the y-axis, right? And yes, growth changes to decay. Isn't that fun? And if I have a negative in the front here, this is a reflection around the x-axis. Reflection in x-axis. And this was reflection in y-axis. So in this case, for the reflection in the x-axis, the range now would be negative infinity to 0, still that horizontal asymptote. Okay. Any number can be the base of an exponential function, 2, 3, 1/3, whatever, right? But also our favorite number, the natural base, e. Okay, so where does the natural base come from? A lot of real-world applications that involve these equations have, they have this term, 1 plus 1 over x to the power of x, right? This pops up a lot in a lot of equations. Now that equation, 1 plus 1 over x to the power of x, when we graph it, I actually have it right here, right? When we graph it, looks like this, right? So you can see, right? Very cool looking. But over here, something's happening and keeps going and going and going. So why don't we take a look at the limit as x approaches infinity, the end behavior as x approaches infinity. So what happens as x is like, 10,000 or whatever? Well, let's take a look. So here's what I'm going to do. Watch. I'm going to do Control T to get this table up here. But I want to put in my own because I want to literally look at 10,000, right? So here we go. So here's what we're going to do. Menu, Table, Edit Table Settings. Just watch. You don't really have to learn all this right now. This one, the independent, I'm going to say Ask. So now I can type in whatever I want, right? Like 1. Oh, here we go. 2. Here we go. Okay, so what about 10,000? Oh my gosh, what number is that? 2.718. What? That is E, right? So what? Oh my gosh. Okay, hang on. Let's just process this for a minute. So like as this goes further and further and further, it's going to level off at a horizontal asymptote, which happens to be E. So wouldn't you know it? Good old Euler, that's where he came up with this number, right? So that is the natural base E, right? 2.71828 and so on and so on and so on and so forth. We should all know that E is 2.718. However, all of the calculations you're going to do with E, you're going to have a calculator for them, right? Nobody's going to expect you to do any of that by hand. So without further ado, why don't we graph f of x is equal to e to the x? This one you would do with a calculator. However, let's do all the things that we know without a calculator, right? The asymptote, still y equals 0. Nothing has changed. 2 just became 2.718. The y-intercept, f of 0, is e to the 0. Oh my gosh, it's still 1. Okay, so here, why don't we go ahead and put these numbers over here. So here we're going to have e to the negative 1, e to the 0, e to the 1, e to the 2, right? Well, e to the 2, let's go ahead and put all of these in the calculator. And we see that e to the negative 1 is 0.36, it's like 789, so we're just going to do 0.368. E to the 0 is 1. This is 2.7. E squared is 7.4, right? That's a good number to know. Now look, we don't really have to go to that many decimals because when you graph it, you really can't graph the difference between 0.4 and 0.368, right? So, all right, so asymptote goes first. E to the negative 1 is 0.4. Then 1, then 2.7, then 7.4, all the way up here. Oh, wow, way up there. Okay, graph, fantastic. All right, domain, still all real numbers, range, 0 to infinity, and then these, I think you guys are okay now. Right? Continuous everywhere. Excellent. Okay, so let's take a look at this one. E to the 2x plus 3. So now finally we have some a vertical shift. There's some action in this problem. So the asymptote is now no longer y equals 0, it's y equals 3. So remember, what does a vertical shift do? When I shift this graph up, it shifts everything, the point and the asymptote, right? So everything is going to shift up 3. So y is 3. The y-intercept, f of 0, is e to the 0 plus 3. That's 1 plus 3. It's equal to 4. Again, that's something you should be able to do by hand. Let's see what else we can do by hand. The domain, we can do by hand. Okay, the range, it's e to the 2x plus 3. Where is the asymptote here? Right here. Now this is e to the 2x. It's going to sit above the asymptote. So it's going to go from 3 to infinity. Now you're probably asking, well, when is it going to sit below the asymptote? Well, that would be if there was a negative in front of the e right there. Okay? And then, so as x approaches negative infinity, this is going to go to 3, positive infinity, infinity, and then it's continuous everywhere on its domain. All right, so why don't we go ahead and put some numbers and let's graph this. So here we have e to the negative 2 plus 3. This we know is 4. E squared plus 3. Right, so e squared, we said was 7.4 plus 3 is 10.4. We're already going off the grid, so I'm not even going to try the other one. And this one here is 3.1. This is already 10.4, so I'm just going to go there. Okay. All right, so you really should be able to figure all this out without a calculator, but obviously to get the points, you would have your calculator. Okay. Now, let's do some word problems, because what's life without word problems? I'm boring. Okay, so in addition to investments, right, which we've always talked about, remember, like exponential growth, compound interest, and so on and so forth. Well, other things also change at exponential rates, right? Populations of people, populations of animals, bacteria, also radioactive decay, right? Amounts of radioactive material. So here we get into a little bit of notation issues. Your book, for some reason, likes to use these capital N's, which I don't particularly like because the entire world uses Y's. So I have put both here. All right. So remember, so if I have a quantity N, its initial quantity would be N naught. And if I have a quantity Y, its initial quantity would be Y naught. Okay. So exponential growth works like this. If there is an initial quantity N naught, which grows or decays at an exponential rate, then N is the final amount after T, right? So for example, something that grows at the same rate every year, like somebody's salary grows at a rate of 2% or 3% every year, right? N naught is the initial salary, and then after so many years, N would be their final salary, or Y naught and Y. So if we're talking about examples like that, salaries, populations that grow at a fixed rate every year exponentially, we will be using this formula, okay? Y equals Y naught, 1 plus R to the power of T. If this is growing, then R is positive. If it's decaying, then R is negative. So, for example, if something is decaying at a rate of 2%, I would do 1 minus 0.2. Okay. Now, if I have continuous exponential growth or decay, continuous is the key word, then instead of R for the rate, we use K. Okay? Yay. So the equation there is Y equals Y naught e to the KT. This is everybody's favorite, the APERT formula. No, we can't use APERT because the OG, the original equation, is Y equals Y naught. And then bankers, because they couldn't use Y's for some reason and they needed their own special language, said, P for principal, whatever, but we're going to use Y equals Y naught e to the KT. That is the universal equation used everywhere by all mathematicians. And if you ever wanted to get into the cool parties, we got to use this. Okay. So K, if K is continuous growth, then it's positive. If K is continuous decay, then it's negative. Fabulous. Okay. The state's population is declining at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 years. This is declining. That's the most important thing. At a rate of 2.6% annually. So the rate is negative 0.026. Okay. The state currently has a population of 11 million. So we're going to say Y naught is 11 million. Predict the population of the state in 15 years. So if T is 15, we want to find what Y is, right? So this is fixed, right? Not continuous. So we're going to use this equation. Y equals Y naught, 1 plus R to the power of 2. Y equals 11. I'm not going to put up, all the zeros for million, right? We know that this is in terms of millions. 1 minus 0.026 to the power of 15. We all know how to plug this into the calculator. 7.4093. Okay, so now, what is the new population of the state? It's not 7 people. It's 7.409 million people. Or just that's the population. This semester, we are going to stress the rule of, 3 decimal places. Okay? So we're going to go to 3 decimal places. All right. Okay, uranium has a half-life of 704 million years. Okay. Half-life, it is understood that it is continuous growth. So let's add that here for half-life. Okay, we're always going to use those equations. Uranium has a half-life of 704 million years. A, write a modeling equation for the exponential decay of uranium-235. So remember U-235, this is an isotope, and that's how they are denoted by the number of neutrons. So U-235. Okay, so if something has a half-life of 704 million years, it means if there is 1 kilogram of a substance now, 704 million years later, there's going to be half of that. Another 704 million years later, there's going to be half of that, and so on and so forth. So what we're going to do is use this equation, y equals y naught e to the kt. Okay. So, sorry. The half-life is 704 million years. That's our T, 704 million, right? So now, if initially I had y naught of something, 704 million years later, I'm going to have exactly half of that amount. So the final amount is going to be exactly half of what I had before, half y naught. So going here, my final amount is half y naught equal to y naught e to the k times 704, which is my t. I'm doing this because first I need to find k. So the y naughts here will cancel. So I have half is equal to e to the 704k. Okay, so now remember from last year, to solve an equation like this, we take the ln of both sides. Okay? And we do that because the variable is as an exponent of the e. To get rid of that exponential situation, we take the ln of both sides. So now what I have is this, ln of a half is equal to ln and e here neutralize one another, and I have 704k. To solve for k, I divide by 704. So k is ln of a half over 704. And that's exactly how I'm going to plug that into my calculator. Remember, we're not going to round as much. Ln of a half over 704. Okay, so this is what I get. And that number is negative 9.846 times 10 to the power of negative 4. In other words, negative 0.0009846. So what is my equation? That's what I wanted. Y equals y naught e to the negative 0.0009846. Okay, y equals y naught e to the k t. Cool. Let's go to B. How many grams of uranium will be left after 2 million years if you start with 300 grams? This time, my T is this. And starting with 300 grams, that's my y naught. So for part B, y equals y naught e to the k to the power of t, which is 2. So let's go to the calculator. We're not going to round. This is going to be 300 e to the power of this number, right? Just press the up button, times, how much was it? 2. And we get 299.4098. So it's 299.410 grams. Okay, C. Use your model to estimate when 200 grams will remain if you start with 300. So this time I'm given y and I'm given y naught, and I need to find t. So, so here we go. So 200 is equal to 300 e to the negative times t. Okay, so what I'm going to do first is divide by 300. So 2/3 is e to this number Now what do we do? Take the ln of both sides. So this is ln of 2/3 is equal to the k So t is ln of 2/3 over this. Let's see. Oops. Okay, so ln of 2/3 over that t, the k. Here we go. 411.814. So that's how many years? Okay. What did I do wrong? This is all in millions. So million years. 411.8 million years. Okay. Fabulous. Okay, and does that make sense? Well, let's see. We start with 300. We want 200 to remain. Half-life is 700 million years. So if 700 million years had passed, the 300 would become 150, half of it. We're not quite at the half, so we shouldn't be at the 704 million years either. So yeah, that does kind of make sense. Okay? All right. Here we go. This is a table shown for the number of reported cases of chickenpox in the United States in 1980 and 2005. If the number of reported cases of chickenpox is decreasing at an exponential rate, what is the rate of decline? And write an exponential equation to model the equation. So this doesn't say continuous growth. So we're going to say y equals y naught, 1 plus r to the power of t. Okay. So we want the rate of decline, r. Okay, so this is the final one, y, 32.2, is equal to the initial value, 190.9. Remember, these are all in thousands. 1 plus r to the power of the amount of time that has passed is 25. Okay, so we divide by 190.9. 1 plus r to the power of 25. And I'm going to take the 25th root of this. Right, so this one doesn't have any, so it's easier for us to do. Take the 25th root. and we get 0.931 is equal to 1 plus r. And then here, I'm just going to subtract 1. So r is negative 0.069. So that's part A. Part B, when will the number of cases drop below 20,000? So once we see when it'll be 20,000, we can figure out that time. So what is my equation here? Y equals 190.9, 1 minus 0.069, 3 decimal places to the power of t. This time, why don't we do that by graphing? So here, let's graph. Let me clear this. 190.9 times 1 minus 0.069 to the power of x. Okay, so that's the equation. And of course, we don't see it because everything is, way up. So why don't we go over to 50 here? Remember, this is all in thousands. And then the time, right, the year, I'm predicting, it's going to be more than 10 years, right? So why don't I go to 50 here as well? Okay, you can see that graph right there, okay? So remember, we went up to more than 50,000. We went to the right, more than 50 years. And so we want this to be at 20,000. So let me go here, and in Y2, why don't I type in 20,000? Oh my gosh, I should have done 20, not thousand, sorry. Right, because everything is in terms of thousands. So right here, and if I find the point of intersection here, here we go, increase, right? So T is 31.555 years. Okay? All right, and there we have it. Thank you very much, and I will see you guys next class.